So, hi everyone. Uh, Only those people who know about De Bruijn sequence. So there is something called um, De Bruijn sequence. Those who know about this sequence and those who know that this sequence exists, those who know about the theorem regarding De Bruijn sequence, they can solve this problem very easily. So what I feel that this problem solution to this problem is based on your mathematical knowledge. If you know about this thing, then you can solve it. Otherwise, with your own wits, it's hard to solve this. The solution to this problem is based on some other assumptions, based on some already existing theorems. Using those theorems, you can solve this problem. But otherwise, on your own, coming up with some solution is not easy for this problem. So, okay, we'll discuss what De Bruijn sequence is. Um, let's read what problem is. So in problem, you have uh, all the possible substrings of uh, length n, and you have to find its superstring, which consists of all those strings, and that superstring should be of minimum length. The length should be as minimum as possible. Okay. Uh, for now, uh, just assume that we have an array. We have an array, and this is my index 0, this is my index 1, this is my index 2, so on. We have lot of indices, and right now we don't know what is the upper bound of this array. That means we don't know the size of this array. So let us assume this array is of uh, infinite size. Theoretically assume that this array is of infinite size, and you can have as many indices you want in this array. And let's say this array is filled with some unknown characters. So let's say at 0 index we have a, and then b at 1 index, then c, then d, then e, and so on. So the value of a can be anything. It can be the value of a can be 0 or 1 or 2 or 3 or anything. But right now we don't know what is the value of a, what is the value of b, what is the value of c, what is the value of d, what is the value of e. So this array, which is of infinite size, filled with some unknown values. We have unknowns in this array. We don't know what exactly is filled in this array. Now I'll tell you that uh, at each index we can find a, so I'll make us one statement. At uh, each index we can find a string of uh, length n. So at each index we can find a string of length n, and that n can be any length. And let's say n is 3. You can assume any value. N can be 4, n can be 5, but let's say n is 3. Then by n is equal to 3, I can say that at index 0, I have a string of length n, which means a string of length 3. So ABC is that string. So ABC is a string of length 3 and is placed at index 0. Again at index 1, there is a string of length 3 which is BCD. At index 2, I have a string of length CDE. Great. So let's write it. At index 0 we have string ABC. At index 1 we have a string BCD. At index 2 we have string CDE. So one thing is common, that between any two consecutive strings, so you have a string at index 0 ABC and the just next string BCD have something common. So this BC part is also repeating in the next string which is starting from BCD, which is starting at index 1. And these values of ABC can be anything. It can be 0 0 0 or 0 1 0. Any value they can take. So at each index we have a string of length 3. And if we assume one thing, if we assume, so I'm making an assumption here. So assumption is at each index we have a different string of length n, and here we assume that we have taken the n equal to 3. So at each index we have a different length. So this is something I'm assuming. This may not be true, but let us assume that at each index we have a different string. So let's say if a string appears at index 0, which is ABC, this won't appear at anywhere else. So this string BCD, which is appearing at index 1, it won't appear at anywhere else. So at each index we have a unique string, different string, and we are taking n equal to 3. So it is not possible that we can do this till infinity, right? Because there is a limitation on number of possible strings of length 3. And in the problem we are given a k decides what are the possible values of characters I can take. And for now, let us assume that we are working on binary strings. Let us assume that we are working on binary string. For that, k is equal to 2 and value or possible characters are 0 and 1. But let's say let's take in general, don't assume that. So if any random value k, we have 0 1 2 till k minus 1. So at each index you can have value from 0 to till k minus 1. So how many different possible strings you can create? So at each index I have k choices, right? So for a string of length n, at first position I have k choices, then at second position I have k choices, with the last index we have k choices. So total k raised to power n possible strings of length 3 using these k characters. Using k characters, total possible strings of length n are k raised to power n, right? So we have only k raised to power n different strings. So that means in this array, which is keeping different string at each index, at max it can have k raised to power n indices. K raised to power n indices. So in my array, it should not bound to infinity. It should bound to some finite index. At index 0, I have some string. So at index 0, I have a string of length n. At index 1, I have a string of length n. Till last index will be k raised to power n. So you will have a string of length n at index 0. After that, you will have a string of length n at index 1, at index 2, and the last unique string will be placed at index k raised to power. So this is the index k raised to power n. Last string will be placed at here. And to accommodate this string, we need some extra indexes as well. Since each string is of length n, so first character will be accommodated at index n, and we need extra n minus 1 indices to accommodate the last string. Rest of the strings are adjusted by the other indices, but to accommodate the last string, I need extra n minus 1 indices, right? So what will be the size of this array? What will be the size of array? Size will be k raised to power n plus n minus 1, right? So this is the most optimal, so I can say this is my optimal length. Optimal length of what? Of superstring. Because this array consists of all the strings of length n, and it is and that too exactly once. It is not repeating any of the string. It is including each string exactly once. So this is the ideal. We can't minimize the length of this array further. This is the minimum possible length. We can't reduce the length of our superstring. So this array is nothing but this array is my superstring. Superstring is the one which have all these string as substrings. So this is the minimum possible length of array. So if we can find a string, so by now we don't know what is a string, what is my superstring. I don't know what is the answer, but one thing I know that the whatever will be my answer, in that answer the length of that string can't go less than k raised to power n plus n minus 1. Now a mathematician, obviously D. Bruijn came and he said that for any base value k, so we'll call our number k as base, and n as my order. So for any base k and order n, there exists a sequence there for this base k and order n. There always there always exists a sequence which includes all possible strings of order n, or I can say length n, built using uh, characters k, characters from set k, and in that set k I have character from character 0, character 1, character 2, so on till character k minus 1. So every so this is something De Bruijn claimed of, and if we see the example, um, so using this so let's see some examples. So for we'll assume that base is 2, so we'll work only with binary De Bruijn sequences in which characters are 0 and 1 only. Great. So if one says that order is 2, let's if order is 2, then whatever my De Bruijn sequence, at index 0 I will have some string, at index 1 I will have some string, and one thing that you have noticed here or observed here, that to get the if we have a string at, so I can say that if you have a string at index I, so let's say at index I you have a string str1. To get the string at index equals to I plus 1, what you will do? You have to do two things. Remove the first character of string str at index I, and append a new character to this string, right? So here you may have observed that to get this BCD, I've started from ABC, so just drop this first character, and you get what? You get BC, and which is of length n minus 1, right? And to make the string of length n, you have to append a new character here. So you can append anything, so that depends on your possible choices of character. So if you have a choice of only binary characters, a binary string, then you can place 0 or 1 here. You can either place 0 or you can place 1. If you have k equal to 2, then you can if you have k equal to 3, then you can place append 0, append 1, append 2. So depending on the size of your set k, you can append those amount of characters after it, right? So what people do is that by so this array is nothing. So if we follow this assumption makes this array a De Bruijn array. So this assumption is making this array a De Bruijn array or a De Bruijn sequence. So this array is nothing but a De Bruijn sequence because of this assumption. And what people do, use by seeing these D Bruijn sequences, people draw something called a graph which is called D Bruijn graph. People draw a D Bruijn graph. So in a graph, we know that we have some nodes and we have some edges. We have nodes and we have edges, right? In graph, we have nodes and edges, and that graph may be directed or it may be undirected, right? So D Bruijn graph is a directed graph. So undirected, so there is no scope of undirected. So a D Bruijn graph is a directed graph. First of all, D Bruijn graph is a directed graph. And what thing will make nodes in the graph? So let us define what is node in the graph, D Bruijn graph, and what are the edges. So nodes are the all possible strings of length, or we can say order n. So all those possible strings, here you can say A, B, C and B, C, D and C, D, E, these three strings. These possible strings which are placed at each index, they will become node of my graph. And how will you define the edge? So edge connects consecutive strings. So edge will connect string at index I with string at index I plus 1. So here I have string at index I, and here I have string at index I plus 1. Okay, and how it will connect? It will connect with that extra character that you are appending. So the new character that you are appending to transform string at index I to string at index I plus 1, you are appending a new character to the string at index I. So that character is placed at the edge of between those two connected nodes, right? So let us take an example and draw the graph. So let's say k is 2. So you have a binary D Bruijn graph. So you have a choice of character 0 and 1 only. So for n equal to 2, let's start with node. So yeah, I have a string 0 0. Let's start with a string 0 0. Now, so let's say this is at index I, right? So at index I, at general index I have this string 0 0, which is of length 2. Now at index I plus 1, I will connect a string. So for that, what you will do, you will drop this first character, and you get a n minus 1 length. So n minus 1 is 1 here, and you have to append a new character here. So how many choices you have? You have a choices of 0, you have a choice of 0, you have a choice of 1. If I append 0 here, I will get a new string that is 0 0. But 0 0 is already present here. So what you can say that if I append 0 to this string, then I will be at the same node, because on appending 0 at index I plus 1, I am getting 0 0 only. But if I append 1 here at index I plus 1, I'll get a string of 0 1. So if you append 1, you will get a new string that will become a new node, and that will be of that will be 0 1. Again, so at this node I had only two choices, 0, either append 0, either append 1. On appending 0, I was at the same place. On appending at 1, I got new string, that is 0 1, and obviously we are dropping this first character and appending a new character, dropping the first character and appending a new character. So let's do this with this node as well. So drop this first character and append a new character. Let's append 0. But you'll get 1 0. So 1 0 is not covered anywhere else. So it will become a new node. So we got a new node of string 1 0. On appending what? On appending 0. If I append, if I drop 0 and append 1, I'll get a new string on appending 1, that is 1 1. Right? Now in this node, if I append 0, drop this and append 0, what you'll get? You'll get 0 0. But 0 0 is already present. So that means there is a connection from this node to this node. If you append 0, you will reach here. Right? And if I append 1, just drop this and append 1. What you'll get? You'll get 0 1, and which is also present here. So there is a connection from this to this as well on appending 1. What about this node? If I drop 1 and add 1, I'll get a 1 1. So this is a new string. So far these nodes do not have any 1 1. So no, it will go to itself. So 1 1 is already here. So if I drop 1 and append 1, I'll get 1 1, and 1 1 is already present. So 1 1 will make it here. And if I append 0, I'll get 1 0. So which is here. Now tell me, what are the total number of unique possible strings you can make of length 2 with these two choices? So at index, at first position I have 2 choices. At second position I have 2 choices. Total 4. So here k is 2 and n is 2. So total 4 unique strings are possible. And in this graph, all those 4 unique strings are covered. All those 4 unique strings are covered. So to get your super string, you just need that order of these unique strings which exist on a single path. So I will introduce a new term here, something called Hamiltonian path. So how do we define Hamiltonian path? It is a path which covers each vertex exactly once. So can you find any path in this de Bruijn graph? So this is a de Bruijn graph. For n is equal to 2 and k is equal to 2. So can you find any path in this graph which covers every single vertex exactly once? So yes, we can find. Start with this node, follow this edge and go here, follow this edge and go here, and then follow this edge and go here. So this is one possible Hamiltonian path, right? What if I start from here but go to this string? Then I got stuck. I can't go to this because there's no directed edge from here to here. Either I have to go again to here or I have to go to here, but that will repeat the vertices. So if I choose this path to this path and to this path, then it is possible to get each vertex at exactly once. But instead of choosing this node, if I choose this node, then I got stuck here and I have to repeat either this vertex or this vertex, right? So if Hamiltonian path is present, then that means we can have that superstring which is of length k power n plus n minus 1. And how can I get the superstring using this graph? So this graph we have created using those rules of de Bruijn sequence array. So if I want to get the de Bruijn sequence from this graph, if first of all find the Hamiltonian path, find a Hamiltonian path. So that you can do by doing so this makes a different problem. You have given a graph, you are given a graph, and you have to find a Hamiltonian path in that graph. For that you can make DFS call. If that single DFS call is able to traverse every single vertex, then keep that path, and that path will be your Hamiltonian path. So by observing here, I can say that from 0 0, first choose this edge 1 and go to 0 1. Then choose the edge with value 1 and go to node 1 1. Then choose edge with value 0 and go to string 1 0. So what we will do, at index 0 I will place this string, at index 1 I will place this string, at index 2 I will place this string, at index 3 I will place this string. So let's do it. For that, I have index 0, I have index 1, I have index 2, and I have index 3. Place 0 0 at index 1, index 0. So I place 0 0. So at index 1, starting part is already there, 0 0, but I just have to place 1 here, then 1 1. So 0 1. At index 1 I have got 0 1, at index 2 I got 1 1, and index 3 I have to just place extra and I did extra index for the rest of the to place the rest of the characters of last string. So one thing you can say that you can create an empty you can create a string str and initialize it with the first vertex, your source vertex. This is my source vertex. So initialize it with 0 0 and search for the path, Hamiltonian path. So this is my source vertex. Initialize your string with the value of the source vertex and start finding the Hamiltonian path. And whenever you encounter new vertex, so on adding 1 I got new vertex, just add the value of your vertex. So in this 0 0, In this 0 0, I traversed the edge 1. So since I traversed edge with value 1, so uh, append 1. Now I got here at this node. Now I have chosen the edge with value 1. So whatever is the value of edge, just append it here. Again I chose edge with 0, so append 0. So start with the value of source vertex. So store the source vertex string in your answer strings. This is my answer. And whenever you encounter the new node, just ask yourself which edge you have chosen. Since I have chosen the edge with 1 value, so append 1. Again, have you chosen the edge of 0 or edge of 1? I have chosen the edge of 1, so place 1. So after that you just have to uh, place all those. And since de Bruijn sequence is cyclic, this last node is connected to first node, right? And to get this node I have to append, I have to choose, I have to drop this and append 0. So this will represent my given answer. So this will have 0 0 0 1 1 1 1 0. Okay, I should not choose this. So this much is enough because 0 is already covered, so I don't have to connect it. Right, so 0 0, then 1, then 1, then 0. Right, so 0 0 is covered, 0 1 is covered, and 1 0 is covered. Right, so this is my super string that we want to get. So what, but now you must be wondering, do we find Hamiltonian path in uh, every possible value of k and n? Because another question is that for any value of k and n, you can draw this de Bruijn graph, right? If I give you, let's draw one more graph. So let's draw one more graph, and this time also I'll take k equal to 2, but I'll take n is equal to 3, right? So for n is equal to 3, let's just start with this string. So total possible strings for 3, this is 2 raised to power 3, and that is 8, right? So total 8 possible string will be in my graph, right? So let's draw, let's say 0 0 is one string. If I append 1, what I'll get? I'll get 0 0 1. And if I append 0, I'll get 0 1 0, right? So for the same rule that we have used while generating this graph, just drop the first character and append new character, right? And if I append 0 to it, I'll be at same place, right? And if I append 1 to this node, I will make 0 1 1. Now if I append 0 to this node, I'll get 1 0 0. If I append 0 to this node, I'll get 0 0 triple 0. And if I append 1, I'll get this, right? And if I append 0 to this node, I'll get 1 1 0, right? And if I append 1 to it, I'll get triple 1. If I append 1 to it, I'll get 1 0 1, right? If I append 1 to it, I'll get 0 0 1 0, and if I append 1 to this 0 1 0, I'll get 1 0 1, right? And if I append 1 to this, I'll get this 0 1, and if I append 0 to this, I'll get 1 1 0. If I append 1 to this, I'll be at the same place, and if I append 0 to this, I'll be at this place, this string. So can we find any Hamiltonian path in this graph? So if I traverse this node, then throw this edge, go to this node, 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 then this node, then this node, and this node. And yeah, we have traversed through this path. We have traversed. So this is the path which covers every single vertex exactly once. So we got the Hamiltonian path. We got the Hamiltonian path. And Hamiltonian path has always length n plus k raised to power n minus 1. So the answer to our problem depend upon the existence of Hamiltonian path. So this array which we started with infinity index, we got reduced it to k plus n minus 1 by assuming that at each index we have a unique string, and to get the unique string at each index, we need to find this Hamiltonian path. So if we can find Hamiltonian path, then we can have different index at each different string at each index. So if Hamiltonian path exists, then we can have a sequence which is array over there having different string at each index. So at each index we can have different string. We don't repeat any string, and that will be a super string of minimum possible length. We can't reduce the length of my superstring beyond that. Now, how to say that Hamiltonian path exists or not? So I have searched many resources, but I didn't find any for any given value of k and n. I have a de Bruijn sequence of de Bruijn sequence is denoted by b of k comma n. So I have a de Bruijn sequence. And for corresponding to that, I have a de Bruijn graph, right? So for a given k value n, for any general k value n, so user will give me k, user will give me n. So for that I have this is a theorem which says that there will always be a de Bruijn sequence for any given kn, and there will always be a de Bruijn graph. So from that sequence I can create the de Bruijn graph. So there will always be a de Bruijn sequence. Existence of de Bruijn sequence is same as saying that Hamiltonian path exists. So existence of Hamiltonian path gives the existence to de Bruijn sequence. So existence of Hamiltonian path gives existence to de Bruijn sequence. And I found no proof to that. We have to just take it as a mathematical fact that it happens, that it is a theorem. It is people believe that this happens. So I tried to find, definitely there will be a proof, but I didn't find any satisfactory answer to that. So the problem is hard. This problem is hard because of this proof only. It is very difficult to come up with the proof of this proof of this problem. There are very advanced mathematics people used. They have converted this Hamiltonian cycle to Eulerian cycle, and then they did something to uh, prove that in general, for any value k and for any value n, there exists a different sequence. To solve this problem, you just need the belief. That for any given value of k and n, the different sequence exists. If you believe this mathematical fact without worrying about the proof, then you can solve this problem. But if you worry about the proof, then you have to search for the proof. But right now I don't have the ability to prove this. If anyone knows the proof to this problem, please let me know.